Thanks very much to Gord Miller's office for organizing this event and also for the invitation to speak to you. My story is, moving downscale from the national level to the provincial level, and now I'm going to be talking to you about what I'll refer to as a cottage industry. This is an operation at the University of Toronto, a cottage industry in the scale of the number of people who are involved in pursuing it, but it happens to be a cottage industry that's supported by a massive financial investment by the province of Ontario. The work I'll describe is actually has to do with climate downscaling using dynamical downscaling methodology, but focused entirely on the province of Ontario. And there's already been a number of comments about the importance of getting down in scale in order to be policy relevant. Going down in scale using dynamical downscaling methodologies implies a huge requirement in terms of computational capability. So when I talk about the massive investment that Ontario has already made in the little cottage industry, which is going on at the University of Toronto, I'm talking about the SciNet facility, which exists as a data center in an old warehouse that used to be occupied by a newspaper way up on Keele Street, north of Highway 407. In that warehouse, there currently exists about $40 million, going on $70 million worth of computer equipment. And the SciNet operation is running, funded almost entirely by the province of Ontario over the past 5 years with a budget of about $50 million. So this is the level of the capability that's required to pursue this dynamical downscaling methodology. And so here what I want to do is to describe to you what we're able to do using this methodology at the provincial scale. So our goal, of course, is to actually get down to a scale which is truly policy relevant. And the idea of using a regional climate model to do this, embedded within a global model of the kind that the Environment Canada person has talked to us about, to be really policy relevant, we'd like to get down to a scale maybe even on the order of a kilometer. We're not quite there yet. But I'm going to describe to you results which get down to 10 kilometers, heading towards 3 kilometers, which is really at the nub, I think, of policy relevance. That's really where we need to be. And what I want to describe is what you gain from this. And what you gain from this, particularly in the province of Ontario, and I'm going to basically demonstrate to you that basically on the global scale, even on the scale of 50 kilometers, models don't even see the lakes. Okay. This is a big problem for Ontario. We have these awful lakes which modify our landscape enormously. So where we're headed actually in this project is actually to focus on water availability, water resource availability in the Grand River Basin. But I'm going to take a slightly larger scale view of this work for the purpose of this talk. Past funding for this work has come from OME from 2010 to 2012, and most recently from the IBM SOCIP consortium, which also has a huge BlueGene Q machine, it's called, IBM BlueGene Q machine in the SciNet data center. Okay, so basically what we're trying to do is to go from a global model projection of the warming process, which captures very nicely the polar amplification effect, which you're all aware of, right down to the mesoscale. I mean, for example, we need to be able to predict lake effect snowstorms and the intensity of these storms, which play such a huge role in this entire region. And for this reason, I'm going to focus all of the attention in this talk on precipitation processes. Not just on lake effect snowstorm-related precipitation processes, but precipitation processes in general. What do we gain by going downscale? I mean, you'll understand, all of you who've looked at the climate change literature, that on the global scale, precipitation is a real problem, right? It's kind of at the heart of what's worst about our ability to project or to understand precipitation processes in general. And what I'm going to argue, in fact, is that when you go downscale, our ability to how shall I say, make direct contact with the observational constraints actually improves enormously, especially in this region. So that's basically where we're headed. This is basically the capability that I'm going to describe to you. Those of you who know a little bit about the downscaling process will understand that we start off with a global model, typically now running at roughly 100 kilometer scale. I mean, the previous generation was at about 150 kilometer spatial scale. And we embed within that global model, and I'm going to show you results from double downscaling, where we first embed a continental scale model within the global model, driving it at its boundaries with output, 6-hour output from the global model, and then embedded within that at 10 kilometers resolution. And as I said, we're heading towards 3 in the next step, right? A third model embedded within the global model. But I'm going to concentrate on results that focus on this Ontario and the Great Lakes Basin region at 10 kilometer scale. And the methodology I'm going to apply makes use of a global model, which is actually the NCAR model rather than the Canadian model, in its incarnation called CESM1, which is the Community Earth System Model 1. And then I'm going to use the Weather Research and Forecasting Model, which is called WRF, not the guy in Star Trek or whatever Worf comes from, but the Weather Research and Forecasting Model at 2 resolutions, the continental scale at 30 kilometers, which is even finer than the results which Compute Canada showed us for its regional model for the same area, which was at 50 kilometers, and then going down from 30 kilometers down to 10. And remember, this is a huge computational problem, but because Ontario has seen fit to equip us with the capability to actually do this kind of work, I think the province is in a position, if it chooses to take advantage of it, of building an Ontario-centric capability, which is the equivalent of any capability anywhere. Okay, so this is basically the game. Here's the global model, and we're talking about a 100 kilometer scale global model, CESM1. The RCM we'll use is WRF, and we'll do it in 2 steps, down to 30 kilometers and then down to 10 kilometers. And of course, what we're actually wanting to do is to move up into this regime heading towards 2100. And I'll show you some results for Ontario for the 2100 time frame. But to do this at really fine resolution, we can't afford to actually run the nested set of regional models continuously from the takeoff point right up to 2100. So what we choose to do is to take output from the global model at 6-hour intervals and then to drive the local model for periods of, say, 15 years each at mid-century and at end century. And there's an issue, of course, as to whether that's a sufficient number of years, and that's a technical question, and we address that question in the course of the work that we do. But of course, for Ontario, as I've already commented, the fact that we have these lakes is a terrible inconvenience because none of the global models include anything like a realistic representation of the impact of lakes and the feedbacks from the lakes onto atmospheric processes. So what we've done, and this is actually unique to the work that we've been doing in our little cottage industry, is to employ a freshwater lakes model called FLAKE. It's a European model in which the individual lakes are described by an individual set of one-dimensional versions of the lake, which consist of basically a mixed layer on the surface of the lake and an underlying thermocline, right? But all of the lakes are described in terms of this one-dimensional representation. That is, they don't have individual circulations in the lakes described. But it's turned out to be the case that these lakes are not sufficiently deep that this actually matters that much, okay? Although the climate feedbacks turn out to be extremely important. And of course, for each of the lakes, we need very detailed bathymetries of the lakes, and we have detailed data from the buoys in the lakes that we can compare with model predictions in order to establish credibility. So just a couple of results with WRF coupled flake in the inner domain, right? Basically showing air temperature, surface water temperature, ice in, ice out data. In the first instance for Lake Erie, which is the shallowest of the lakes that we have to work with, and then for the northern part of Lake Michigan, where there are modest errors, right, in the black predictions of the observations, but not, I would say, significant at all for the purpose of the analysis of climate feedback effects. So what do we get from this? Well, the first thing we get from this is the ability on small scale to capture in the validation exercise for the historical period for which we have good data. We're able to predict the existence of every one of the snowbelts that exists in the lee of the lakes. And we're also able now, for the first time ever, this has never been done before, is to actually ask what is the impact of the global warming process on the snowbelts in the lee of the lakes. And if you happen to be a person who's running a ski resort or something, this is something I'm told that you really need to be seriously concerned about. So just a couple of interdomain results for the province of Ontario at mid-century. Changes relative for 2050 to 2060 relative to 1979-2001 over Ontario. So for precipitation increase as a function of month, right? We're seeing increases in terms of millimeters per day on the order of, and you'll see these impacts going forward to end century turn out to be very much more impressive. But at mid-century, we're seeing like something on average of 0.1, 0.15 millimeters per day in terms of precipitation, and a warming, an annually average warming for the province of Ontario at mid-century. And here we're showing both Tmax, Tmin, and T average, Tmean, something between 2 and 2.25, 2.5 and 3 degrees centigrade. And I need to point out to you, and this was already clear in the Environment Canada discussion, right? Because we're on land, right, and because the heat capacity of land is very much less than the heat capacity of ocean, right, even though by 2100, on global average, we expect to see a mean temperature increase of maybe 3.5 degrees or something like that. What we're seeing here is basically that same increase at mid-century. That's because we're on land, mitigated somewhat by the fact that there are these lakes around, but not much. Okay? And here is the again going forward, the future scenario for Ontario, again just to mid-century, and you can see we're seeing, looking at the changes in mean annual snowfall, we pick up all of the snowbelts again, and we're able to demonstrate, and this is actually an interesting physical fact, that you might imagine that because we warm, that the snowfall will go down so much everywhere that all of the snowbelts will be wiped out. But of course what's happening in the system is that because the coverage of the lakes by lake ice in winter is decreasing, right, there's more evaporation from the lakes, and therefore the snowbelts continue to exist, and in fact at mid-century become more intense than they are now, right, which wouldn't be even capable of commenting upon without actually coming downscale into our region and looking in detail at what's going on spatially. Just to make the point as to what a step forward it is in terms of the production of climate change data, this is a paper that just appeared in the journal Science about 3 weeks ago by Alex Hall at UCLA, who's picked up the paper that Jonathan Gula and I published in the Journal of Climate 2 years ago, which first showed this capability. Alex has picked one of the papers, one of the figures out of that, and used it to basically demonstrate the huge advances we're now able to make in terms of dynamical downscaling, using our ability to predict the lake effect as key. So I want to end this last 5 minutes of discussion, with the discussion of extremes, because that's basically what this game is all about, as all of the practical people have been at pains to make clear. When you're designing infrastructure, you need to worry about the most extreme events in order that you can add the appropriate engineering factor in order to ensure robustness. So, of course, there are various ranges of origins, if you like, of uncertainties in these climate change projections. Uncertainty associated with natural variability, uncertainty associated with the nature of the model that you're actually using to make a projection, and finally, this huge uncertainty, as we've already heard discussed, associated with the greenhouse gas scenario that you choose to believe to be the one that's most appropriate to discuss. And I think most of us in this room would believe that the RCP 8.5 business as usual scenario is going to hold true probably for much, much longer than we wish. Okay? So just a brief discussion of what dynamical downscaling can do for you in the context of analysis of uncertainties. So to do analyses of this kind, of course, you need to use ensembles of models, and I'm showing you ensembles can be produced in a variety of different ways, and I'm showing you here results from a paper that is about to appear again in JGR Atmospheres, in which I'm showing you results first for CCM at 100 kilometers resolution on the left, right? And these are mid-century results, these two, and for 5 different members of what I call a physics ensemble, and what we've done is to change the representation of cumulus parameterization. We've changed the representation of the parameterization of boundary layer processes we use. We've changed the representation of land surface processes that we use, which are all imperfectly known aspects of the standard physics package, which would be a part of a standard either global or regional model. So physics is also a source of uncertainty, right? Because none of these representations are exactly known. They're all parameterizations. So let me just walk you through. Here are the 5 members of the mini ensembles. I'd call it a physics mini ensemble. Here is another 5-member mini ensemble for mid-century, in which what we've done in the GCM is to include the impact of very rapid sea ice removal in the Arctic, right? More rapid than you might imagine to be the case. And in this particular calculation at mid-century, the impacts are clear in the Hudson Bay region, okay, but less clear elsewhere. Here's basically end century of this set of temperature field results, and you can see again reinforced this idea that at end century we're looking at the province of Ontario at an increase in mean surface temperature which is on the order of 7 to 8 degrees centigrade, okay? So when you look at the global projection, you're talking about, say, 2.5 to 3.75 degrees centigrade, more than double that on our landmass. So you need to understand the severity of the predictions that we are obliged to accept when you just shift from global down to the regional level. And now you're going to swat me, I think, almost immediately. But I want to talk about these IDF curves just for a minute, okay? Because of course we can capture these as well using the dynamical downscaling process, right? At whatever resolution we're able to afford to run at, okay? And what I'm showing you here is effectively the IDF curve, or the return period curve, basically for precipitation over Ontario, using a method that involves assuming a cutoff. What do you call an extreme event? And we're calling every event in the data sets we have available that's in the top 2.7% in intensity to be extreme. And then what we use in the observational data is to look at the probability distribution, right, for that observed data set. We then produce the same data set using the dynamical downscaling, the same representation using the dynamical downscaling calculation. And you can see on the right-hand side, comparing black to blue, right, that we fit basically the return period data using the dynamical downscaling methodology. So we've got beautiful control, which most people who've thought about precipitation process in climate would find to be really very surprising. Okay? And so when we move forward here to mid-century, and this is from a paper that just appeared about 2 months ago, right? We're on the red curve, and the 50-year event has now shifted from 100 millimeters per day to 150 millimeters per day, and the 20-year event to 102 millimeters per day, and you can see basically the comparisons here between the forward projection of the IDF curve. I've just been told that my time is up. I'm about to be hung out to dry, but just to summarize in this last slide, okay? So again, precipitation amplitudes of 50-year events are increased by 14 to 29% by mid-century. The current 50-year events will occur more frequently, every 25 to 15 years. So we're able to get a direct measure of the impact on the IDF curve of the use of the dynamical downscaling methodology at very high resolution. One last comment that I will make, okay, is that there's an extreme event at 2100, okay, in this 5-member physics ensemble, and it's shown here. It's model little g, and the result is associated with the land surface process version of the physics package, and it's showing basically all of the models basically show, of course, increasing dryness in the U.S. Southwest. So the droughtiness, if you like, of the U.S. Southwest under global warming, of course, becomes more and more and more extreme, right? But depending upon the land surface model, that droughtiness impact on precipitation over the province of Ontario can become extremely extreme because basically water recycling in the precipitation field is basically eliminated by the extreme drying in the land surface model, right? So this is just to make the point that the analysis of extremes is extremely important, right? And there's a great deal more scientific work that needs to be done to further embellish the ensemble so as to make so as to come to a much clearer understanding as to whether extremes like this are actually plausible or whether they are completely implausible, right? And this is very important work. But just to end, I'll just comment that we're in a position here in Ontario now to do work at this, what I would say is the highest level, basically in the use of the dynamical downscaling methodology to generate very high quality results on climate change projections. And I would just say that although it's been commented earlier in the meeting, first thing in the meeting, that there's a huge amount of climate data out there. That's true. There's too much climate data out there because there's no quality control on most of it, right? And so I think, you know, what I'd like to see happen in the province is for the government to accept the responsibility for trying to build an organization, the goal of which is to produce the best quality climate change projections that it can do for the use of the province's population. So thanks for your attention.